Welcome back to Blockchain, the animated course, Unit 2, Ethereum, Smart Contracts, and your first steps in Solidity. Every Solidity topic comes with real, compilable code, explained line by line. Here's the roadmap. Unit 2, Topic 1, the Ethereum blockchain. Unit 1 gave us an incorruptible shared ledger, but Bitcoin's ledger speaks exactly one sentence: X paid Y some coins, powerful and limited. 2013, Vitalik Buterin publishes the Ethereum white paper with one radical question: what if blocks carried programs, and the network executed them for everyone, identically? 2015, Ethereum goes live. The ledger becomes programmable. Every rule you can write in code can now live on chain. Bitcoin is a calculator, brilliantly engineered to do one thing: move coins, with bulletproof reliability. Ethereum is a smartphone, the same secure foundation, but anyone can install apps on it. The apps are called smart contracts, and the phone never turns off. That's why Ethereum is nicknamed the world computer, one giant computer whose memory is replicated on thousands of nodes, running programs nobody can secretly stop or edit. Ethereum has two kinds of accounts. First, the familiar kind, an externally owned account, an address plus a balance, controlled by whoever holds the private key. That's you, Alice, Bob. Second, the new species, a contract account. It has an address and a balance too, but also code and storage. And crucially, no private key exists. Nobody logs into it. Its own code is the only thing that can move its money. Where does contract code run? On the EVM, the Ethereum virtual machine, a single, standardized processor specification. That every node runs identically, same code, same input, same result, on thousands of machines, so the network can reach consensus on program results exactly like it does on payments. Running code on thousands of machines isn't free. Enter gas. Think of a taxi meter. Every single instruction the EVM executes ticks the meter. You pay for exactly the computation you use. Worked example. A plain Ether transfer costs exactly 21,000 gas. At a gas price of 20 GWI, the fee is 21,000 times 20 billionths of an Ether, 0.00042 ETH. More complex code, more gas. And the killer feature: a transaction carries a gas limit. If code tries to run forever, it runs out of gas and is rolled back. Infinite loops can't freeze the world computer, they just run out of fuel. So an Ethereum transaction can do three things: move Ether, call a function on a deployed contract, or deploy a brand new contract. Two of those didn't exist in Unit 1. Worked example: Alice calls buy ticket on a lottery contract, attaching 0.1 Ether. Watch the full journey. Step 1. Alice signs the transaction with her private key, same signature mechanics as Unit 1. Step 2. It waits in the mempool, the network's shared queue of pending transactions. Step 3. A validator includes it in a block, exactly like any payment. Step 4. Now the new part. Every node's EVM executes buy ticket, independently. The contract's code adds Alice to the players list and accepts her 0.1 Ether. Step 5. The contract storage, its player list, its balance, updates identically on every node, sealed under the block's hashes from Unit 1, state agreed, worldwide. That's the Ethereum blockchain, Unit 1's ledger plus accounts that are programs, one shared virtual machine, and a gas meter to pay for it all. Now, what exactly is one of these on-chain programs? Unit 2, Topic 2, Smart Contracts. The definition to memorize: a smart contract is self-executing code, stored on a blockchain, that automatically enforces the terms of an agreement. Cryptographer Nick Szabo coined the idea back in 1994, 2 decades before Ethereum gave it a home, and his original explanation is still the best one. A vending machine is a contract. Insert $1, press B4, receive the snack, But notice what's missing: a shopkeeper. The machine doesn't trust you, and you don't trust the machine. The rules are welded into the mechanism. A smart contract is a vending machine made of code, living on the blockchain, holding real money. Compare a paper contract. It's just a promise. Enforcement lives outside, lawyers, courts, time. A smart contract doesn't promise, it executes. A Kickstarter with no Kickstarter. Backers send Ether straight to a contract. The rules: goal 100 Ether, deadline 30 days. Our code, visible to everyone. Path A. The goal is reached. The contract releases the funds to the creator. No one approves it. The code just runs. Path B. The goal is missed. Every backer is refunded automatically. Nobody can run off with the money, because the code physically cannot do anything except these two paths. Autonomous and self-executing. When its condition is met, the contract fires by itself. No middleman pulls the trigger. No clerk forgets. No manager delays. Deterministic. Same input, same output, on every one of thousands of nodes. That's what makes consensus possible. It's exactly why EVM code can't roll dice or call the internet. Those would differ per node. Immutable. Once deployed, the code can never be edited. That's the guarantee. And the danger. In 2016, a bug in a contract called the DAO let an attacker drain about $60 million, and nobody could patch it. Code ships with its bugs. Distributed. Like everything on the blockchain, the contract lives on every node. There is no server to unplug, no company to shut down. Transparent and verifiable. The code and every execution it ever performed are public. Don't trust the crowdfunding contract? Read it. Trustless and tamper-proof. Two strangers can do business through it, and nobody, not even the person who wrote it, can interfere with an execution in flight. Fast and cost-reducing. Settlement takes minutes instead of days of paperwork, and the middlemen who each took a cut are simply not in the loop. Accurate. No manual retyping. No clerical slips. One caveat to carry from characteristic 3. Code is law cuts both ways. A bug is enforced just as faithfully as a feature. 8 characteristics. 1 sentence. A smart contract is a vending machine's certainty combined with a blockchain's permanence. Time to learn the language they're written in. Unit 2. Topic 3. Solidity. Introduction. Solidity is to the EVM what a recipe is to a kitchen robot, a human-readable language that compiles down to bytecode the machine executes. It borrows JavaScript's look and C++'s strict types, and lives in .sol files. Your first complete, real, compilable smart contract. Simple storage. It stores one number on the blockchain, forever, for everyone. Let's read every line. Line 1. A machine-readable license node, required by the compiler since code on a public chain is, well, public. Line 2. Pragma, the compiler version contract, $0.819 means compile me with 0.8x, no older. Version 0.8 matters. It added automatic overflow protection to all arithmetic. Line 4. Contract declares the unit, like a class in other languages. Everything inside is what gets deployed to that contract account we met earlier. Line 5. A state variable. This is the magic line. Stored number doesn't live in RAM. It lives on chain, replicated on every node, surviving forever. Private means other contracts can't read it directly. Line 7. An event. A log entry the contract can emit. Apps outside the chain. Websites. Wallets. Listen for these to know something happened. Lines 9 to 12. The set function. Public means anyone can call it. It writes to storage. And writing on chain costs gas. This is a transaction. Mined into a block like any payment. Lines 14 to 16. The get function. Note view. It only reads state. Reads don't change anything. So they need no transaction. No block. No gas when called from outside. Writes cost. Reads are free. The EVM doesn't read Solidity. The compiler, Solc, turns your .sol file into 2 artifacts, Bytecode, the raw EVM instructions that get deployed. That 0x6080 prefix opens nearly every real contract on Ethereum. And the ABI, a JSON menu telling apps what functions exist and how to call them. Write Solidity, compile to bytecode plus ABI. Deploy the bytecode to a contract account. In Unit 3, we'll do that deployment for real, with Truffle and MetaMask. First, the vocabulary of the language itself. Unit 2, Topic 4, Solidity, Datatypes. Analogy for this chapter, type lockers. Every state variable is a locker with a fixed shape, and the compiler flatly refuses to shove a boolean into a number-shaped locker. Strict types equals fewer expensive surprises. 1 contract, every core value type. All of this is real Solidity. Let's open each locker. Bool, true or false. Perfect for flags like is active. Default value if you don't initialize. False. Solidity 0 initializes everything. There is no undefined. UINT8, an unsigned integer squeezed into 8 bits. 0 to 255. We set it to 255, the absolute ceiling. One more and it would overflow. UINT 256, the workhorse. Range, 0 to 2 to the 256th power, -1, a 78-digit number. When in doubt, use UINT 256. The EVM is built around 256-bit words. Underscores are just readability separators. Int 256, the signed variant. Negative numbers allowed. Use only when you genuinely need values below 0, like a temperature or a balance delta. Address, a 20-byte Ethereum account identifier, and meet MSG sender. Inside any function, it's the address of whoever is calling right now. Here it captures the deployer as the owner. You'll see this idiom in every real contract. Address payable, same 20 bytes, 1 extra power. The contract may send Ether to it. Plain address can't receive transfers. The type system forces you to say who may be paid. Bytes 32, exactly 32 raw bytes. The natural shape of a hash kekak 256 is Ethereum's fingerprint function. SHA-256's cousin from Unit 1. The real value here, 0x5 a 1329 df95 f63d0b. String, dynamic UTF-8 text. Flexible but expensive to store and compare on-chain. Pro tip you'll see everywhere. Store the bytes 32 hash of text when you only need to verify it, not display it. Locker Demo 1. Try to store -1 in a UINT. The compiler rejects it before your code goes anywhere near the chain. Cheap failure, best failure. Locker Demo 2. Push a UINT 8 past 255 at runtime, and Solidity 0.8's built-in guard reverts the whole transaction. Before 0.8, this silently wrapped to 0, the exact bug class that drained real contracts. That's why our pragma says 0.8. 10 types. 1 rule. Pick the shape that makes illegal values impossible. Next, what you can do with them. Operators. Unit 2. Topic 5. Solidity. Operators. Operators are the same symbols you know from any language, but here every operation runs on thousands of machines and costs gas, and a rounding surprise can cost real money. 6 families, each with live examples. Addition, subtraction, multiplication, power, modulo, all familiar, except line 3. 7 divided by 2 is 3. Integer division truncates, because Solidity has no floating point at all. No decimals, no floats, so money lives in Way, the smallest unit, 10 to the 18th Way per Ether. All Ether math is integer math on Way. Remember 7/2 equals 3, it will save you real funds someday. Comparisons return bools, and their natural habitat is the require statement. Require, balance, equals price, is the bouncer at the door of every real payment function. And, or, not, with short-circuiting, in is active and value, 0. If the first check fails, the second is skipped entirely. In Solidity that's not just style, skipped work is gas saved. Bitwise operators work on the raw binary. Shifting 5 left 1 bit doubles it to 10. You can see the bit slide. Niche. but they power gas-optimized tricks and flag packing in production contracts. Compound assignment, plus equals, increment, and the ternary, condition, question mark, value if true, colon, value if false, an entire if else in one expression. 6 families, 1 habit, whenever you write a slash, hear a voice whisper 7/2 is 3. Next up, custom types, starting with enums. Unit 2, Topic 6, Solidity, Enum. Analogy, a pizza order tracker with exactly 5 allowed stamps. An enum is a custom type whose value can only be one of the names you list. Every illegal state becomes literally unrepresentable. Lines 2-3, the enum declaration. Status now is a type, like unt or bool, and a status variable can hold placed, baking, out for delivery, delivered or cancelled, nothing else, ever. Line 5, under the hood an enum is just a small unt, placed is 0, baking is 1, and so on, so the default value is the first member, a new order starts as placed automatically. The advance function, the require guard blocks moving past delivered, then line 9 does the enum 2-step, cast status to unt, add 1, cast back, placed becomes baking becomes out for delivery. And cancel, only allowed while the order is still placed. Once the oven's on, there's no backing out. Business rules, enforced by types and requires. Drawn as a diagram, the enum plus its guards form a state machine. Green arrows are advance, the red one is cancel, and no other movement can exist. Delivered and cancelled are dead ends by design. Hold on to this picture. In Unit 4, entire private blockchains are modeled as exactly this. State machines with rules for legal transitions. You've just built your first one, in 11 lines. Unit 2, Topic 7, Solidity, Arrays. Analogy, egg cartons versus conveyor belts. A fixed array is a 12-egg carton. Its size is part of its shape. A dynamic array is a conveyor belt you can keep loading, but every step you walk along it costs gas. Line 2, a fixed array, unt bracket 3, exactly 3 slots, known at compile time, cheaper to reason about. The egg carton, 90, 85, 77. Line 3, a dynamic array, empty brackets. It starts empty and grows on demand. The conveyor belt. Add, calls scores push, s, bolt a new slot onto the end of the belt, costs gas. You're permanently growing on-chain storage on every node. Remove last, calls pop. The last slot is removed and its storage cleared, which actually earns a small gas refund for cleaning up the chain. Count, returns scores length. Dynamic arrays always know their size. First, read scores, 0, 0 indexed like C or JavaScript, and the comment matters. Index out of bounds doesn't return null, it reverts the whole transaction. Strict, like everything here. Live run, add, 70, add, 88, add, 95, 3 pushes, 3 new slots, indices 0, 1, 2 length is now 3. Remove last, pop takes the 95 off the end length, 2, and scores, 5. Right now, instant revert, transaction cancelled, as if it never happened. One more distinction the exam loves, memory versus storage. A memory array is scratch paper for one function call, cheap and temporary. A storage array is carved into the chain itself. Strings and bytes? They're arrays too, with the same rules. And a warning that leads straight into our final topic. A user-growable array plus a loop that walks all of it is the classic gas bomb. Why? Loops are next. Unit 2, Topic 8, Solidity, Loops. Analogy, a running track where you pay per lap. Solidity loops look exactly like C or JavaScript, but every iteration burns gas, and if the tank empties mid-race, the entire transaction reverts. Loop design is money design. The for loop, initialize I at 0, run while I is under the array length, increment each lap. Note pure, this function touches no state at all, it just computes. Also note the named return total, declared in the signature, returned automatically. The while loop, same engine, Different dashboard. You manage the counter yourself. This one walks the belt until it finds a value over the limit, and returns early, leaving the loop the moment the answer is known. Saves laps, and laps are gas. Lap 0, I is 0, XS, 0, is 3, total becomes 3. Lap 1, total climbs to 8. Lap 2, total 17, now I becomes 3, the condition I, 3 fails, the loop exits and 17 is returned, 3 laps, 3 gas payments. Third variant, do while, the body runs first, the condition is checked after, so it always executes at least once. Rare in contracts, but it's in the toolbox, and inside any loop. Break exits early, continue skips to the next lap. The promised gas bomb. In the wild, a lottery pays every player with a loop. With 50 players, fine. But the players' array keeps growing, and one day the loop needs more gas than a block can contain. Now the payout reverts every time, for everyone, forever. Real contracts died exactly this way. The professional pattern, pull over push. Instead of one giant loop paying everyone, each winner claims their own prize in their own small transaction. Loops for computing, not for mass paying. And that's Unit 2. You met Ethereum, the world computer, with its virtual machine, its 2 kinds of accounts, and its gas meter. You know what a smart contract is and its 8 characteristics. And you've read real Solidity, a full contract, every data type, every operator family, enums, arrays, and loops, including the gas bomb that kills careless ones. Next time, Unit 3, the advanced half of Solidity, mappings, structs, modifiers, exception handling, inheritance, and we deploy a real contract with Truffle and MetaMask. See you there.